So it's great to be here. And from the last talk, I remember when I just arrived at Microsoft, sending Steve Ballmer an email, which the title was Towards a Carbon Neutral Microsoft. That was long before the days of people knew about carbon footprints. I forget what Steve replied, but now we do actually have a good policy in Microsoft, and Microsoft has a relatively small carbon footprint. However, anyway, so what I want to talk about today is, as Andrew says, about the impact of digital data in all fields. So I will talk about science, but I also want to relate it to the digital humanities, and I also want to say how people can get involved, how you can excite kids in science and technology, and how classes and schools and people can get engaged in doing worthwhile things with their computers, with their resources, to help science on its way. Okay, so thousands of years ago, people were looking up at the stars, not with telescopes, to actually understand the planets and so on. And that was the beginnings of experimental science. And lots of the data was written down and until the 1600s, when people like Newton, like Galileo, like Kepler and so on, began the beginnings of theoretical science, summarizing all that experimental data in some laws of physics for which you could predict new events and new things. And so those are the two methodologies of science for many years, until in the last few decades, computational science has come of age. And what this shows is a multi-core chip. These are now processors, multiple processors on a single chip. And computation is the only way we can look at climate change. It's the only way we can look at galaxy formation, for example. So that's accepted as now a new methodology. You need to know different skills, architectures, algorithms, numerical methods in order to play the game of computational science. And what we're seeing, we believe, Ken Wilson, Nobel Prize winner in physics, called computational science the third paradigm. And what Jim Gray, who was my colleague at Microsoft, believed, that we're seeing the emergence of a fourth paradigm. And the fourth paradigm is data-intensive science, and it's typified by this slide here from the Sloan Digital Sky Survey. That was a multi-year survey which looked at a quarter of the night sky and literally looked at millions of galaxies and millions of objects in that survey. And since there are only about 10,000 astronomers, it's a curious change of model. Instead of actually publishing your study on a particular star, which is how astronomers did. I should say astronomers are fairly strange people. You know, we classify people as chemists, physicists, and so on. Astronomers are very strange. They classify people by wavelength, all right? Visible, X-ray, ultraviolet, radio, and so on. So I'm just showing the visible here, but there are large amounts of data. So the fourth paradigm, data-intensive science, is a new way of looking at things. And what you'll find in the bookstore is a book we put together of scientists with computer scientists looking to the future. I had them write essays. They don't usually write essays, short essays, actually giving their vision of the future. And so, for example, in environmental science, there's a great article by Jeff Dozier, which looks at the fact that you've gone from earth science to earth system science, and now you actually have to use that science to actually solve some of the problems facing humanity. He calls it the science of environmental applications. So scientists actually need to go and do things. So this is dedicated to Jim Gray, and there are copies in the bookstore. It's free. It's published under, it's the first Microsoft book published under a Creative Commons license. You can download it for free. It also has a Microsoft part number, and I asked Mike why that was. It's so you can do print on demand. So you can get a print on demand copy, and there will be versions for the Kindle and Sony ebook. So we're trying to actually give people's visions of where science is going in the future. And there aren't enough copies for everybody, so it's first come, first serve. Otherwise, you can download it on the web. So, Curtis Wong at Microsoft developed the Worldwide Telescope, which was to enable ordinary people and scientists to go and look at all this massive data. And the Worldwide Telescope picks up data from all the different wavelengths, so you can look at Spitzer, you can look at radio waves, you can look at the microwave background and all this sort of stuff. And in addition, you can have tours by famous scientists to say that this galaxy, and you can look at it in various wavelengths and look at star formation and so on. So it's a very compelling experience. And it's been used by a group at Oxford to develop what they call Galaxy Zoo, which is citizen science. So you have 1 million galaxies in there, say, and how do you classify them? Do you classify them as spherical, or do you classify them as elliptical? Do you classify them as spiral, and so on? Are they spiraling to the left or the right, and so on? And so what they've managed to do is enthuse 200,000 or so volunteers to spend their time classifying galaxies. And it's not just a wasted exercise, because this is an example. This object here is a very strange blue object. It's the bluest galaxy ever known. Astronomers don't really know what it is, and they've now asked for Hubble space-time to go and look at it in more detail. It was discovered by Hanny van Arkel. Voorwerp is Dutch for object, and this is actually, she's a school teacher in real life, and this is actually really directing astronomers to go and try and understand this very strange object. And in addition, recently, there's been another scientific paper published about these funny little things here. These are called green peas, and the astronomers not only looked at pictures, but they actually looked at the spectra. And these are very strange galaxies. There aren't very many of them, and they would not have been found without the efforts of all these hundreds of thousands of volunteers. And they are galaxies which have a particular characteristic of being very effective at producing stars. So, green peas. So citizens can do real science. And you'll be able to see and have a play with Worldwide Telescope on a portable planetarium on Saturday, and you'll be able to go and do some cool manipulation with hand manipulation of the images and zoom in and zoom out. So I hope you'll enjoy that. There are other types of citizen science. This is another example. This is from chemistry, protein folding, and this is a game. It's been formulated as a game, and people who are good at games can actually go and challenge themselves compared to real scientists at seeing how molecules dock with the three-dimensional. So you can, if you want to check for a potential candidate for a drug to stop a molecule working, you can see if it docks in particular ways, and you can adjust its orientation and so on. And that's in a game called Fold It. And again, it's a game where people can get engaged and find possibilities that professional scientists may not yet have found. This is another project that I did actually in the science program that we're also working with, climateprediction.net. It's relevant to you. And you can do it again with whole classes. So what they had is 400,000 or so volunteers running a climate model from 1950 to 2050. Why do you want 400,000, you say? Well, it's because the parameters of the starting point in 1950 for your computational model weren't all well known. And the question is, does a small variation in this parameter affect the final result, or a small variation in that parameter? And so you can give a whole class of kids, for example, a whole different set of starting parameters, run the model on their home PCs or their PCs in schools, and you can see what the global warming is predicted. And so they have a paper in Science or Nature which shows that the majority of parameter starts of the 400,000 gives you, 2 or 3 degrees warning, but there are some sets of parameters. These parameters, these change a little bit. You can get higher, 8 or 9 degrees, and some give you lower. So it's an interesting new way of looking at climate prediction, which can really inform the way people think. So those are examples from Curtis Wong, a colleague at Microsoft Research, and he's really been thinking hard. You have lots of potential technologies to put together to make a game or to make a telescope or whatever. How do you make it so people actually learn and want to know more? And so he has this model, engagement, context, and reference. So you have to sort of tell a story. So that's, if you like, a professional astronomer tells a story about galaxy formation or whatever. And then you have to give the context. And so you give extra context around that. And finally, you have to allow people, when you've engaged them, you've drawn them in, You allow them to go and access reference material like Wikipedia or professional databases, whatever you want. So that's the model he uses to build, and I'll use it to illustrate in the next slide. We used in an interesting thing called Project Tuva. Bill Gates, some years ago, was on a vacation and took a physics video on his vacation. That's Bill, all right? And he had a great time. He took the Feynman video and thought it was really great. So he looked at all 7 of these things. They were done in 1960 in Cornell. They're a really inspiring set of lectures. And what we did, Bill negotiated personally, nothing to do with Microsoft or his foundation, to get the access rights for showing these videos. So now we can stream them to anybody. We can't give you them, but we can allow them to be streamed. And rather than just showing a black and white video of Feynman in the 1960s, talking rather formally, what we thought we'd do was try and give you a richer experience. And Curtis Wong developed this system using the same principles that I've enunciated. So these are the 7 lectures. I should add that the lecture on probability and uncertainty about quantum mechanics was the basis on which I actually wrote a popular book on quantum mechanics. I used this as a starting point. But so you can look at the lecture. So you could just look at the black and white lecture if you want. But you can do more than that. And what this shows here is under the bottom. Is there a pointer? No. All right. You can zoom in where you like along the lecture. In addition to seeing the lecture, you can go and find out about particular figures. So this is about Römer and defining the velocity of light. You can actually go and do links to the actual search to the text of the lecture. So you can actually have a transcript, and you can search here. You search for Kepler, and you find 7 places in the lecture where he mentions Kepler. You can click in it and go to that point in the lecture. You can actually go and link to a simulation. He talks about spiral galaxies, so you can go and, this was in the 1960s, you can go and look, for example, to Worldwide Telescope or a simulation of a galaxy. You can link to external resources outside of the lecture material. And of course, you can add notes. And so particularly if you're a lecturer, you can use this material, you can add notes and link to particular data resources that you want. Or you can get the whole transcript, and it's linked with videos and so on. So it's a way to provide, Feynman provides the engagement, but then you can find more about the context, and then you can find lots of reference material. So that you can find on the web, and it really is still, you know, nearly 50 years later, it's really a compelling experience. Feynman was truly amazing. He is my hero. So that's digital data in the sciences. It really is changing things. But also, what about humanities? When you're doing archaeology, you'll digitize the site quite frequently now. How do you engage? How do you do these things? So I'd like to show you a short video of how you can use it in archaeology. So if Mike will show for Microsoft Asia, I'd like to show this video showing how you could use rather sophisticated research technologies to do things that you can't do. You create a digital version of the object. So a short video.
Each nation's heritage represents its past glory, its present identity, and its future inspiration. In July 2008, Microsoft Research Asia launched the unique eHeritage program that applies the latest computing technology to digital preservation, virtual restoration, and the interactive display of unique historical treasures. The eHeritage Initiative preserves cultural heritages through the application of advanced computing research. Let's explore some of our key technologies. The original beauty of ancient objects may be obscured by 1,000 years or more of weathering. With the Microsoft Appearance Manifolds technology, objects can be viewed at each stage of the weathering process in a virtual world. Priceless jade objects are often sealed in museum display windows. Microsoft proposed the first GPU-accelerated diffusion equation technology, enabling screen presentation of lifelike translucent images of jade and light, supporting touch-based interaction and full-angle viewing. Museums use high-resolution digital cameras for archiving their ancient paintings. The gigapixel digital camera invented by Microsoft can create digital images of over 1.6 gigapixels at a reasonable cost. These photographs are more than 6 times sharper than the images the human eye generates. The concentric mosaic has been applied to the virtual terracotta warriors that provides the richest possible 3D experience without requiring a scene's geometric information. In addition to inventing key research and enabling technologies, Microsoft is also partnering with academia on heritage preservation. The Bayon Temple in Cambodia presents an enormous challenge to create a digital model at a 1 centimeter resolution. We provided the Windows-based cluster, which dramatically reduced the processing time for this huge amount of image data. Animating Chinese paintings immerses users in the beauty of Chinese traditional culture via play. Now we are collaborating with universities and museums to annotate one of the greatest Chinese traditional paintings and to virtually represent the 3,000-year-old Mao Gongding. Microsoft Research looks forward to working with computer scientists and domain experts in preservation to further protect and promote historical assets through our eHeritage program.
Thank you, Mike. So that's using some rather fancy technology. What I'd like to talk about is a more democratic technology that you can do with school kids, you can do with professionals or whatever. And this is a project we did in India on the Sri Andal temple, and what it did was enabled a team of students went out and took 6,000 photographs and videos, and they put together what's called a photosynth. So it's a 3D world you can create from lots of different people's photographs. It can actually figure out what the three-dimensional structure and allow you to explore it, allow you to zoom in and out. And so you can do that with video, and you can stop. It looks like a video, but you can actually stop and explore and go and see where you got to. You don't have to follow where the video went. You can actually go and explore. So it gives you a new way of looking at these digital artifacts. So this is using a number of technologies, but in particular photosynth. And so we thought we'd demonstrate that by actually doing a photosynth. And so after dinner last night, Mike collected lots of photographs taken by the people here to create a photosynth of PopTech, and just to show you the sort of things that you can do. Mike? Okay, so this is you, all right? And so you can actually go and walk around the different photos. You can actually, it's a collage of all these different photos, and you can zoom in and see me scratching my ear or whatever it is, and you can zoom right out, and you can see, can you show the point cloud? So you can show actually how it reconstructs from all these photographs, these different images, and you can see where the individual photographs were used, and you can actually construct this arena virtually. So it is the sort of thing that you can get people engaged. People can go and take photographs. You can do field trips. You can take things of Monticello. You can take, pictures of the White House. And I don't know if you saw the Obama inauguration. They did a huge photosynth on CNN. So thank you very much, Mike. So what we'd like to do is invite you to go and thank you very much, Mike. I think it's possible with all this digital data now and tools that you can make available for you to go and experiment and engage in projects like climate prediction, like Galaxy Zoo and so on, and do meaningful science. And I think that's a really good thing to excite people, the potential of science and technology. And you can go and have a look at Project Tuva. We'll try and release that as a kit that you can do to your videos, and you can actually annotate and enrich your videos. So we think it's actually a good tool for making teaching remotely more interesting. And you can, of course, go and create your first photosynth. So you can actually, after the end of this conference, we'll try and put all your photographs there to create a wonderful photosynth of PopTech, and it's your photosynth. So have a look, visit us online. These are all free. So thank you very much for listening.